Equilibrium and torque problem. Example number 4. Here we have a good old-fashioned teeter-totter. We have a 30 kilogram student at the left end, a 20 kilogram student at the right end. The teeter-totter is 3 meters long. The fulcrum is the point at which it rotates up and down. And that's movable left and right in this particular case. What we want to do is figure out where it would balance given these conditions, and the fact here now that the board itself has a mass of 45 kilograms, which needs to be factored in. Like all torque problems, what I'm going to do is draw the simplified free body diagram first, just drawing a horizontal line with all the forces involved. What we have here now is a student at the left end who's 300 newtons, a student at the right end who is 200 newtons. I should have drawn that arrow a little bit shorter. Alright, and then the board itself is 450 newtons. In this case, since it's a uniform teeter-totter, that means its center of gravity is geometrically in the center, 1.5 meters from each end, and it's a weight of 450 newtons. That's geometrically centered for the moment. I will write down the numbers in a second. But what we have here is the fulcrum. The fulcrum is pushing up, is holding the whole thing up. I'll symbolize that with a blue arrow. And it's going to be a little bit left of center because the heavier person is to the left. The fulcrum has to be a little bit left of center. If the fulcrum were right in the middle where the 450 Newton force was, the big kid would go down and the little kid would go up, and we wouldn't have equilibrium until the big kid hit the ground. We want this to balance horizontally. Now that blue arrow there, the upward force by the fulcrum, will need to be the sum of the 450 plus the 300 plus the 200. That's going to be 950 newtons. So we know all forces involved already because we have translational equilibrium. The up forces, or force, has to equal the down forces. Alright, so we have that. Now, I'm going to label all 4 of our points, and we don't always have 4 forces. You're going to see some examples here in a few minutes where there's 2 forces, or 3 forces, or 10 forces. Well, we won't do anything with 10 forces, but there could be any number of forces here. Well, at least 2. But here's another example with 4. I'm going to label the points A, B, C, D, and I can pick any one of those 4 points to calculate my torque. In this case, I'm going to pick point D here, C in a few minutes here, just to show you can pick any location you want. But some are better than others. In general, you want to pick a location that you know how far it is from the other forces, or you want to pick a location where there's an unknown force so you can get rid of that force, as you saw in the previous example. But this will come with practice. I'm going to pick point C here in a minute, but the numbers here, as far as distances involved, from C to D, is, I believe, 1.5 meters. That's 1.5 meters. That's how far it is from C to D. It's also the distance from A to C. Let me use blue. A to C is also 1.5 meters. I just don't know how far it is from B to C. And that's the one thing that we're looking for, actually. Really the only thing we're looking for. But I'm going to calculate my torque with reference to point C. I want my clockwise torque equal to my counterclockwise torque. Once again, you can just use a capital T. You don't need to make them squiggly on top like the tau. But clockwise torque equals counterclockwise torque. Okay, the struggle once again is going to be, okay, which way is clockwise? Well, we know clockwise is the way the hands of the clock go, but how does that translate to this diagram? Well, we're going to call point C our fixed point, and it's kind of like the middle of our clock where all the hands are attached. And this is like the second hand that has extensions on both sides of point C. For example, if I hold point C fixed and I pull down at point A with 300 newtons, the whole point A will go down. If point A goes down, point D goes up, and if point C, well, point A and D are moving, or can move, the whole thing spins around point C. That's our reference point. At point A, though, if we pull down with 300, the whole thing will spin counterclockwise. So the 300 Newton force is a counterclockwise producing force, torque. And then point D is the opposite. So point D then is going to be a clockwise producing torque. It's going to be 200 newtons times the distance from point C of 1.5 meters. And also the 950 Newton force is pushing up at point B. It's real close to point C, but it would also help the 200 Newton force to make the whole thing spin clockwise. If point C is held fixed and everything else is allowed to rotate, point B would go up and rotate around point C clockwise. That's a 950 Newton force times a distance that we don't know. We're going to call that D. And it's hard to show that here, but this is going to be, that little space there is D. It's how far it is from B to C. So the torque for the 950 Newton force is 950 times that distance D times the sine of 90, which is 1, so we're not going to write that, equals our counterclockwise torque, which we already mentioned before, will be the force at point A pulling everything, or point A down and rotating around point C, force of 300 newtons times the distance of 1.5 meters. So what we have here is 300 plus 950D equals 450. Subtract the 300 from both sides, divide by 950. I believe you end up with D equals 0.16 meters. That's how far point B is from point C. Alright, so you'd say something to the effect of the location, where should the fulcrum be placed, 16 centimeters left of the center of the board, 0.16 meters. So the answer is 16 centimeters left of the center of the board. You could figure out that would be like 1.34 meters from the heavier student. Here's another fun torque problem. This is a mobile, the kind that would hang above a child's crib, like when you're a baby. The black stuff here on the top is supposed to be the ceiling. And then we have weights that are at the ends of horizontal bars. The horizontal bars are not massless. They have some mass, 25 grams each. And we're given that mass 1 is 150 grams. And all the distances are labeled in blue. And there are vertical strings holding up the horizontal bars. They have a tension, T1 and T2. The technique on this problem, same as the other techniques, is to simplify, but we have to do this one in 2 stages. Starting, in this case, the best place to start is on the horizontal, the bottom bar, because we know that M1 is 150 grams. So I will redraw the bottom bar, the free body diagram for the bottom bar, and it has mass 1 hanging down here. It's 150 grams. Well, here's another little trick. You can just leave these in grams. Technically that's not a weight. It's not a weight, it's not a force. But if you leave these in grams, it's not really cheating. These all come out in grams. You don't need to do the conversions. You can always do that later. Call that M2, and we will have to do some converting later. But T1 is pulling up. This is going to come out in grams, not newtons. We'll convert to newtons. You'll see how this works out. Alright, and the bar itself though is 25 grams. Once again, like in the last problem with the teeter-totter, you can put the entire weight, what you need to do is put the entire weight of an object at its center of gravity. This is a uniform horizontal bar, so its center of gravity is dead center, geometrically speaking, and we have 25 grams right there for the weight or the mass of this bar. Alright, once again we do have 4 locations. Let me highlight them. A, B, C, D. A, B, C, D. And I know where all those locations are based on the above diagram. and the fact that point C is the midpoint of that horizontal segment. Let me label all these. This is without the units. This is 20. From B to C here will be 5 centimeters. From C to D will be 25 centimeters. Because from B to D is 30 centimeters. Alright, so we're going to calculate the torque. And in this case, it's probably best to pick point B or point D. Let's pick point B as our reference point. Point B and D are the better points to pick because that, well, point B in this case will now eliminate T1 as a consideration in our torque calculation. We want our clockwise torque equal to our counterclockwise torque. Well, if we pick point B as a fixed point, if we look at this problem, say point D with respect to point B, holding point B as like the middle of our clock, and this horizontal rod can spin like the second hand or minute hand of a clock, point D is trying to make the whole thing rotate clockwise, and so is the force at point C. They're both pulling down. If you let this thing, if you like got rid of M1, if you let M1 cut it off, the 25 and the M2 would pull the whole thing down, or actually clockwise. The whole thing would spin clockwise if point B was still attached to the rope. So those are going to be clockwise generating forces, and I'm going to write that down then. It's going to be 25 times the distance of 5, that's how far it is from point B, measuring everything from point B, plus M2, which is our unknown, times its distance, which is 30, once again from point D to point B, equals then the force or the mass at point A, 150, it's 150, times the distance of 20. So the only unknown there is M2. If you work this all out, you end up with M2 equal to, I believe, 96 grams. So that's part of what we're looking for. And you see how if we had converted everything to newtons, that would have come out in newtons, then we'd have to divide by 10 to figure out the mass in kilograms. But this was good enough, 96 grams. It's actually faster. However, with T2, we have to figure out the tension in that rope. Now, the upward force T1 has to equal to the downward 3 forces, the 150 plus the 25 plus the M2, which now is 96. If I add those 3 numbers up, if I take the 150 plus the 25 plus the 96, those are all down, that gives me 271 grams down. Now, you can't really say 271 grams up, but that's a total weight of 0.271 kilogram, or total mass of 0.271 kilograms, which is a weight downward of 2.7 newtons. That's what it does weigh. It weighs all those masses, the 2 masses plus the weight of the bar, is 2.7 newtons. So therefore, T1 must be 2.7 newtons. T1 equals 2.7 newtons. Now the top bar. I'll draw that up here on the top. Top bar. It has T1 pulling down. T1 is 2.7 newtons in weight, which we know, but back in grams, it's 271 grams. So we'll continue to do this, violating the rules of units for the moment, making sure we keep track of that when we give our actual answer. We have M3, which we're looking for, the mass of the bar itself, which is 25 grams, and then T1 pulling up. This will be very similar, or that's actually T2 now. This is very similar to what we just did with the lower bar, so I'm going to go a little faster. I'm going to highlight our 4 locations. Let's call this E, F, G, H, And I know all the distances, once again, I'll do those in blue. From E to F is 10 centimeters. From G to H is 30 centimeters in this case, because the whole bar is 60 centimeters long. Point G is dead center, because it's a uniform bar. And from F to G, this is not to scale, would be 20 centimeters, because from E to G must be 30 centimeters. All right, so once again, well, let me pick point, well, let's pick point F again as my reference point. It'll make it very consistent with what we did with the lower bar. So point F is where I will reference for my clockwise torque balancing with my counterclockwise torque. Alright, so let's look at point F. It's just like the lower bar. The clockwise will be the 25 grams, pulling down, trying to make the whole thing rotate around point F clockwise. Same thing with M3. Let me use blue here, or let me use black. So we have 25 times the distance of 20 times the sine of 90, plus M3 times its distance of 50 centimeters from H to F, equals the counterclockwise torque, 271 times 10. Alright, if you multiply that all out, follow the rules of algebra, M3 comes out to be 44 grams. Alright, that's good. Figured that out. Now we have to figure out T2. We'll figure that out just like we did T1. We need to add the 271 plus the 25 plus the 44. That would be, I believe, 340 grams of mass, which would be 0.374 kilograms, which would then weigh 3.4 newtons. That would be the weight of all that mass on that string number 2. So therefore, T2 equals 3.4 newtons. That's how tight that string is. And we've finished this problem.